The closest star to our Sun is only 4.24 light-years away. That word "only" might be the most misleading word in astronomy. Because 4.24 light-years equals roughly 25 trillion miles. If you placed a human crew on the fastest interstellar probe ever launched and pointed it straight toward Proxima Centauri, that crew would have been gone for more than 70,000 years before the ship ever arrived. And strangely, that is still the simplest part of the problem. The real difficulty begins when you try to face everything that exists between here and there: radiation that slowly tears apart human DNA, engines that can never carry enough fuel to slow down, life support systems that would need to operate perfectly for longer than most civilizations have ever existed. The unsettling truth is not just that the stars are distant. It is that even the nearest one may still lie beyond our reach. So take a moment, settle in, and let your thoughts slow down. Now, let's dive in. On August 24th, 2016, the European Southern Observatory held a press conference that quietly reshaped the direction of human ambition. Scientists revealed they had discovered a planet orbiting Proxima Centauri, the closest star to our Sun. Not a gas giant, not a frozen world drifting in the outer darkness, but a rocky planet, roughly sitting within the habitable zone where liquid water could, in theory, exist on its surface. Proxima Centauri b. The discovery sent a wave through the scientific community and quickly captured global attention: an Earth-sized world orbiting the nearest star. The phrasing almost forms itself. The nearest potentially habitable world, right next door, almost within reach. It felt like something inevitable, as if the universe had placed a second Earth at the shortest possible distance, quietly inviting us to come and find it. For anyone who had ever looked up at the night sky and wondered whether humanity might one day walk beneath alien stars, Proxima b seemed like an answer. Not a distant idea hidden deep within some far galaxy, but a real destination tied to the nearest star we know, a place we could name, observe, and aim our instruments toward. A world so close that the light reflecting from it began its journey only 4 years and 3 months ago. But there is a difference between a place you can point to and a place you can truly reach. And it is within that gap that this story shifts, from quiet inspiration into something far more unsettling. Proxima Centauri is a red dwarf star located 4.24 light-years from Earth. It is the closest star to our solar system, part of the Alpha Centauri triple star system that dominates the southern constellation Centaurus. This system contains 3 stars. Alpha Centauri A is a yellow star, slightly larger and brighter than our Sun. Alpha Centauri B is an orange star, a bit smaller and cooler. These 2 stars form a tight binary pair, orbiting one another every 79.9 years, at distances ranging from roughly 11 to 36 astronomical units. The third member, Proxima Centauri, is a faint red dwarf, with only about 12% of the Sun's mass and around 14% of its diameter. It orbits the central pair at an immense distance of approximately 13,000 astronomical units, taking more than 500,000 years to complete a single orbit. Proxima lies slightly closer to us than its 2 brighter companions, making it the nearest individual star to our solar system, though only by a narrow margin. The discovery of Proxima Centauri b was not accidental. It came from years of precise observation using a method known as Doppler spectroscopy. As a planet moves around its star, its gravitational pull causes the star to shift ever so slightly, creating a subtle wobble. That gentle wobble shifts the star's light toward red as it moves away from us, and toward blue as it comes closer. By carefully tracking these tiny changes in Proxima Centauri's light spectrum over many months and years, astronomers at the European Southern Observatory identified a repeating signal with a period of about 11.2 Earth days. That signal pointed to a planet with a minimum mass of roughly 1.07 times the mass of Earth, orbiting at a distance of around 7.4 million kilometers from its star. Because Proxima Centauri is much dimmer and cooler than our Sun, This tight orbit actually places the planet inside the habitable zone, the region where temperatures might allow liquid water to exist on a rocky surface. Since that first discovery, more planets have been found within the system. Proxima Centauri d, a smaller world with less than Earth's mass, orbiting even closer to the star, was confirmed in 2022. Another planet, Proxima Centauri c, was reported in 2020, though its existence is still debated due to possible noise in the data. The system continues to be studied, and many details about Proxima b remain uncertain. We still do not know if it has an atmosphere, or whether it possesses a magnetic field strong enough to protect that atmosphere. We do not know if the powerful stellar flares, common for red dwarf stars, have stripped it down to bare rock. Proxima Centauri is an active flare star, releasing bursts of ultraviolet and X-ray radiation that could be devastating to anything exposed on the surface. So Proxima b could be a living world, or a scorched and lifeless one, or something in between. That remains an open question. But none of this changes the core fact that captured global attention. There is an Earth-mass planet in the habitable zone of the nearest star. It is the closest known exoplanet to our solar system, and the temptation to think of it as reachable is almost impossible to resist. 4.24 light-years. Say it quickly, and it sounds manageable, like a number on a road sign or a delivery estimate. 4.24. The decimal makes it feel neat, contained, almost small. Compared to the scale of the galaxy, it is small. The Milky Way stretches roughly 100,000 light-years across. The nearest large galaxy, Andromeda, sits about 2.5 million light-years away. Against that backdrop, 4.24 light-years feels like almost nothing. A small step on an endless staircase that reaches toward the edge of the universe. But a light-year is not a unit meant for human intuition. A light-year is the distance light travels in 1 year, moving at 299,792 kilometers per second. In 1 second, light travels a distance equal to circling Earth more than 7 times. In 1 minute, it moves beyond the orbit of Mars. In 8 minutes, it reaches the Sun. In about 5.5 hours, it passes the orbit of Pluto, and then the scale changes completely. After leaving the outer edges of our solar system, light enters interstellar space, and the next point it reaches is Proxima Centauri. The light leaving our Sun at this very moment will not arrive there for 4 years, 2 months, and about 17 days. 1 light-year equals approximately 9.46 trillion kilometers. Multiply that by 4.24, and you get the distance to the nearest star. In miles, that becomes roughly 25 trillion. In astronomical units, where 1 unit equals the distance from Earth to the Sun, Proxima Centauri lies about 268,770 astronomical units away. That is 268,770 times the distance between Earth and the Sun. To begin understanding what that truly means in physical terms, rather than just numbers, consider this. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object ever created. After nearly 5 decades of continuous travel, it has reached a distance of about 165 astronomical units from Earth. It moves through interstellar space at roughly 17.3 kilometers per second, which is about 62,000 kilometers per hour. At that pace, Voyager 1 covers around 550 million kilometers each year. That sounds extraordinary, until you compare it to the distance to Proxima Centauri. At Voyager 1's current speed, the journey would take approximately 73,000 years. To place that in human perspective, that is about 10 times longer than all of recorded human civilization. By the time Voyager 1 would arrive, the entire history of writing, agriculture, cities, empire, science, industry, and spaceflight would fit into only the first small fraction of that journey. Now consider the Parker Solar Probe, the fastest spacecraft humanity has ever built. During its closest passes to the Sun, it reaches speeds of about 191 kilometers per second, or nearly 690,000 kilometers per hour. That is fast enough to travel from New York to Los Angeles in roughly 20 seconds. At that maximum speed, the trip to Proxima Centauri would still take about 6,700 years, far faster than Voyager, yet still unimaginably long. Even that is longer than the time separating us from the construction of the Great Pyramid at Giza, longer than the combined histories of ancient Egypt, Greece, Rome, the Middle Ages, the Renaissance, the Industrial Revolution, and the Space Age, repeated several times over. And it is important to remember that the Parker Solar Probe only reaches that speed briefly during close approaches to the Sun, as it swings through the solar corona along a highly elliptical orbit. No spacecraft can maintain anything close to that velocity in deep interstellar space. No propulsion system currently in use can sustain such speeds across the distances required. These are not just abstract figures. They are hard engineering limits that define the boundary between what humanity has achieved and what the nearest star actually demands. We have sent probes past every planet in our solar system. We have landed machines on Mars, on Titan, even on a comet. We have driven robotic vehicles across the Martian surface for years. Yet all of these achievements took place within a region roughly 50 astronomical units from Earth. The nearest star lies at about 268,000 astronomical units. The distance between our farthest accomplishment and our nearest stellar destination is not simply a gap. It is a vast divide, so immense that everything humanity has ever crossed fits inside it thousands of times over. The Alpha Centauri system has fascinated scientists long before the discovery of Proxima b. Alpha Centauri A and B are among the most studied stars in the sky, partly because they are close to us, and partly because they resemble our Sun closely enough to suggest the possibility of habitable worlds. Alpha Centauri A is a G-type main sequence star, the same class as our Sun, about 10% more massive and roughly 50% more luminous. Alpha Centauri B is a K-type star, slightly cooler and dimmer. Together, they form one of the best understood binary systems in astronomy. Proxima Centauri, by contrast, is far smaller and much dimmer. It emits only about 1,600th of the Sun's luminosity. You would not be able to see it with the naked eye, even though it is the closest star to Earth. Its faintness is the reason it was not discovered until 1915 by astronomer Robert Innes at the Union Observatory in South Africa. All three stars are gravitationally linked, yet separated by enormous distances. Alpha Centauri A and B orbit each other relatively closely, but Proxima Centauri circles them at such a vast distance that, for decades, some astronomers questioned whether it was truly bound to the system or simply passing through the same region of space. Observations have since confirmed that it is gravitationally bound, but the sheer scale of this system highlights something essential as the story unfolds. Even within a single star system, distances can be overwhelming. Proxima Centauri orbits its companions at roughly 13,000 astronomical units. Meanwhile, our entire solar system, out to Neptune, fits within about 30 astronomical units. The Alpha Centauri system reminds us that even our nearest cosmic neighborhood operates on scales far beyond human experience. The excitement surrounding Proxima Centauri b is entirely understandable and scientifically justified. Discovering an Earth-mass planet in the habitable zone of the nearest star is one of the most important findings in the history of exoplanet research. It means that the closest possible destination for interstellar exploration is not just a star, but a star with a world that could, under the right conditions, support liquid water. Because of this, every major space agency and many independent research groups have studied or proposed missions to the Alpha Centauri system. But proximity is a relative idea, and the word nearest creates a kind of illusion that hides the physical truth. When we say Proxima Centauri is the nearest star, We are describing its position in a ranking, not its accessibility. It is simply the closest among hundreds of billions of stars in the Milky Way. Being first on that list does not mean it is close in any practical sense. Imagine standing at the edge of the Pacific Ocean and being told that the nearest land across the water is 5,000 miles away. You could accurately call that the nearest point. You might even imagine reaching it one day. But standing there without a boat, without fuel, and without any proven way to survive the journey, the word nearest begins to feel less like reassurance and more like a challenge. This effect becomes even stronger when combined with the discovery of Proxima b. Suddenly, the destination is not just a star, but a world, and not just any world, but one that might resemble Earth. The human mind, shaped by millions of years of exploration on Earth, naturally connects this to every frontier we have ever crossed. We crossed oceans. We reached the poles. We walked on the moon. It feels natural to assume that the nearest star is simply the next step in that progression. What this intuition overlooks is that every one of those frontiers existed within the same gravitational neighborhood. The moon is about 1.3 light seconds away. Mars, at its closest, is around 3 light minutes away. The Voyager probes, the farthest objects we have ever sent, are about 22 light hours from Earth. Proxima Centauri is 4.24 light years away. The shift from light hours to light years is not a gentle step forward. It is a sudden vertical rise in the scale of distance, a break so extreme that every method and technology that carried us across the solar system simply stops working. Consider the energy alone. The kinetic energy of a moving object increases with the square of its speed. If you double the speed, you need 4 times the energy. To reach 10% of the speed of light, roughly 30,000 kilometers per second, a spacecraft would need to move about 1,700 times faster than Voyager 1 today. The energy required to accelerate even a relatively small spacecraft to that speed is not just enormous. It is on the scale of the total annual energy consumption of entire nations, and even that calculation assumes something unreal. Perfect efficiency. No energy lost as heat. No extra mass for fuel. No allowance for course corrections or slowing down at the destination. In reality, the situation becomes worse. Far worse. The rocket equation, first described by Konstantin Tsiolkovsky in 1897, defines the core relationship between a rocket's exhaust velocity, the mass of its fuel, and the speed it can ultimately reach. That equation is exponential. For any given exhaust velocity, increasing your target speed demands an exponential increase in fuel. Chemical rockets, with exhaust velocities of roughly 3 to 4.5 kilometers per second, encounter a hard limit long before they approach interstellar speeds. Even nuclear thermal rockets, which can achieve about twice that exhaust velocity, still cannot escape the exponential burden imposed by the rocket equation at these scales. To accelerate even a modest payload to just a few % of the speed of light using conventional rockets would require fuel masses that exceed the payload by thousands or even millions of times, depending on the system. This is not a question of funding or political ambition. It is a fundamental constraint written into the physics of motion itself. Every kilogram of fuel added to a spacecraft increases the total mass that must be accelerated. That added mass then demands more fuel, which adds even more mass. The cycle feeds into itself. At a certain point, adding fuel no longer helps you move forward. It becomes the main obstacle preventing you from getting there at all. This runaway effect is why every serious concept for interstellar propulsion moves beyond traditional rockets and turns toward more radical ideas. Nuclear pulse propulsion, fusion drives, antimatter engines, laser-driven sails. Each of these represents a different attempt to escape the limits of the rocket equation, either by using energy sources far more powerful than chemical fuel or by removing onboard fuel entirely. And yet, even the most promising of these concepts, the ones studied seriously by engineers rather than imagined in fiction, still result in travel times measured in decades at best, and centuries at worst. For a journey to Proxima Centauri, not one of them has been built. Not one has been tested at full scale. None exist today beyond theoretical models, computer simulations, and small experimental setups in laboratories. The distance to the nearest star does not just challenge what we can build today. It challenges technologies that may take generations to even begin to exist. There is, however, a way to make this distance feel less abstract and more real. Imagine shrinking the sun down to the size of a basketball. At that scale, Earth becomes a tiny grain of sand orbiting about 26 meters away. Jupiter would be like a marble sitting roughly 135 meters from the basketball. Neptune, the outermost major planet, would be a slightly smaller marble, orbiting at about 800 meters. The entire solar system, all the way out to Neptune, would fit inside a sphere about 1.6 kilometers across. Voyager 1, the farthest object humanity has ever sent, would sit only around 4.3 kilometers from that basketball. Now at that same scale, where would Proxima Centauri be? Not across a room, not across a city, not even across a country. Proxima Centauri would be another ball placed roughly 6,900 kilometers away. That is about the distance from London to New Delhi. Everything we have ever explored, every planet, every probe, every mission, exists within a space just 2 kilometers wide, and yet the nearest star lies nearly 7,000 kilometers away on that same scale. Every spacecraft we have ever built is still in the front yard. The nearest star is on the other side of the planet. That is what 4.24 light-years truly means when you translate it into something the human mind can grasp. And this is only the nearest star, not an especially unique one, not an extraordinary destination, just the closest point in an endless field. Everything else in the galaxy is farther, most of it is far beyond comparison. If this is the shortest possible journey between stars, and this is what it demands, then the real question is no longer whether Proxima Centauri exists as a destination. The question is whether any propulsion system we can realistically build will ever be able to bridge that distance. Because right now, even the fastest spacecraft ever created would require thousands of years to make the trip. And the technologies that might reduce that journey to decades still exist only in theory, on paper, inside simulations, or as small-scale experiments. Some of them have not even retained consistent funding, even the most ambitious interstellar project ever proposed. Breakthrough Starshot, aimed only to send gram-scale chips on a one-way flyby. Not a human mission, not a spacecraft that could slow down or enter orbit, not a vessel carrying people who need food, air, and protection, just a tiny chip with a camera, accelerated to 20% of the speed of light, passing the nearest star in a matter of hours and sending back a few images before disappearing into the dark. And even that minimal idea has already encountered engineering limits that ambition alone cannot overcome. The nearest star is 4.24 light-years. It hosts a planet roughly the mass of Earth, sitting in the habitable zone. Everything about that statement sounds like the beginning of a story where humanity reaches outward and succeeds. But the reality hidden behind those numbers tells a very different story. It is a story of distance so vast that it overwhelms every speed we have ever achieved, consumes every form of energy we have learned to use, and outlasts every machine we have ever built. The stars are not hiding from us. They simply exist on a scale that does not align with human ambition, human timelines, or human lifespans. And even the problem of speed, as overwhelming as it seems, may not be the greatest challenge. Every propulsion system we have ever used follows the same basic principle. You expel mass in one direction, and the reaction pushes you forward. Chemical rockets expel superheated gases. Ion engines eject electrically accelerated atoms. Nuclear thermal rockets push heated propellant through a nozzle. The differences between these systems come down to two key factors: how fast they can expel that mass, and how much energy they can extract from each kilogram of fuel. Those two limits define everything a propulsion system can do. And when it comes to interstellar travel, every propulsion system we have ever built falls dramatically short. Chemical rockets, the reliable engines that carried humans to the moon and sent probes across the solar system, produce exhaust velocities of only about 3 to 4.5 kilometers per second. The Space Launch System, the most powerful rocket NASA has built since the Saturn V, generates around 39 million newtons of thrust at liftoff. That is extraordinary for escaping Earth's gravity. But it becomes almost meaningless when you think about reaching another star. A chemical rocket attempting to travel to Proxima Centauri would need to carry so much fuel that the fuel itself would outweigh the payload by an absurd margin. The numbers quickly become unrealistic. You would need a fuel tank larger than an entire planet. The problem lies in the energy density of chemical propellants. Liquid hydrogen and liquid oxygen provide roughly 10 million joules per kilogram. That sounds large, but it is fundamentally limited. Chemical energy comes from rearranging electrons in molecular bonds, and that process releases only a tiny fraction of the total energy stored inside matter. To reach interstellar speeds, you need to go far deeper than that. You need to access the energy inside the atomic nucleus itself. Before moving fully into nuclear concept, it is worth looking at another form of propulsion that often generates optimism, but cannot solve the interstellar problem on its own. Electric propulsion, including ion engines and designs like the Variable Specific Impulse Magnetoplasma rocket, represents a real improvement over chemical rockets. In one key way, these systems achieve much higher exhaust velocities, typically between 20 and 50 kilometers per second for ion engines, and potentially even higher for advanced plasma designs. Higher exhaust velocity means better efficiency. A spacecraft can gain more speed using less fuel. This makes electric propulsion extremely useful within the solar system, where missions can take months or years, and where gradual acceleration is acceptable. NASA's Dawn mission used ion propulsion to orbit two different bodies in the asteroid belt, something that would have been impossible using chemical rockets within the same fuel limits. Within that environment, the technology works remarkably well, but the limitation is thrust. Electric propulsion systems produce extremely low force compared to the mass of the spacecraft. A typical ion engine generates thrust measured in fractions of a newton, similar to the weight of a sheet of paper resting on your hand. Even the most optimistic plasma engine designs would produce only a few newtons. Because of this, these engines accelerate very slowly, building speed over long periods of continuous operation. And for interstellar travel, this creates a severe problem. Even at the upper limits of electric propulsion, reaching 1% of the speed of light, about 3,000 kilometers per second, would require continuous thrust over many decades. To reach 10% of the speed of light, which is often considered the minimum practical target for a human mission to Proxima Centauri, would require thrust lasting for centuries, along with power levels far beyond anything a spacecraft could realistically carry. Electric propulsion trades thrust for efficiency, and while that trade works beautifully within our solar system, it becomes a fundamental limitation when trying to cross the vast distance between stars. The engines that serve us best close to home are exactly the ones that fail us beyond it. To understand just how extreme the energy requirements become, it helps to move away from abstract numbers and picture a real scenario. Imagine a hypothetical interstellar spacecraft with a mass of 50,000 tons at departure. That is already a conservative estimate for a vessel capable of supporting a crew of several hundred people across a journey lasting many decades, including radiation shielding, life support, living spaces, repair systems, and the fuel required to slow down at the destination. To accelerate a ship like this to 10% of the speed of light would require delivering a kinetic energy on the order of 2.25 times 10 to the 22nd joules. And then, to slow it down again into orbit at its destination, you would need to remove nearly the same amount of energy. Just those two phases alone, acceleration and deceleration, would demand a total energy of roughly 4.5 times 10 to the 22nd joules. And that number accounts only for the energy given to the ship itself. It does not include the far greater energy required to accelerate the fuel or to sustain life support, food production, lighting, communication, navigation, and every other system operating over 4 decades of travel. To make that scale more tangible, consider this: the total energy produced by all power sources on Earth, including coal, nuclear, hydroelectric, solar, and wind, adds up to about 5.8 times 10 to the 20th joules per year. The energy needed just to accelerate and then decelerate this spacecraft would equal roughly 78 years of total global energy production. And even that is only the beginning. A rocket must also accelerate the fuel it plans to burn later. And the fuel needed to accelerate that fuel, the rocket equation turns what seems like a large number into something that grows exponentially, depending on the design. The total propulsion energy required can exceed the ship's kinetic energy by hundreds or even thousands of times. The fuel required for such a mission could reach into the millions of tons. The spacecraft would need to carry many times its own dry mass in fuel, along with the fuel needed to accelerate that fuel, and then more fuel to accelerate that additional mass. This compounding effect is why brute force approaches to interstellar travel have never produced a realistic mission design. Nuclear fission. The process of splitting heavy atoms like uranium or plutonium releases around 80 trillion joules per kilogram of fuel. That is about 8 million times more energy per kilogram than the best chemical fuels. This enormous energy density is the reason nuclear propulsion has been considered for interstellar travel since the 1950s. One of the earliest serious proposals was Project Orion, developed in 1958 by physicists Ted Taylor and Freeman Dyson. The idea was simple, though extreme. Small nuclear explosions would be detonated behind a large pusher plate attached to the spacecraft. Each explosion would push the ship forward, gradually building up speed. The concept was mechanically crude, but physically valid. Dyson estimated that an Orion-type vehicle using advanced fusion-based detonations could achieve exhaust velocities of around 15,000 kilometers per second, with a total velocity change of about 20,000 kilometers per second, or roughly 6.7% of the speed of light. That would translate to a travel time to Alpha Centauri of about 130 years. Later studies suggested that even higher cruise speeds, perhaps 8 to 10% of the speed of light, might be possible if no fuel were reserved for slowing down at the destination. The real limitation, beyond the obvious political and environmental impossibility of launching a spacecraft by detonating nuclear explosions near Earth, was the sheer scale of the design. Dyson's interstellar Orion would have weighed around 100,000 tons. It would have required millions of nuclear pulse units. Even for a civilization already familiar with nuclear technology, the engineering demands were overwhelming. The Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space, effectively ended Orion as a practical project, even though the underlying physics remains sound. Later, Project Daedalus, developed by the British Interplanetary Society between 1973 and 1978, refined the idea by replacing fission bombs with inertial confinement fusion. Daedalus proposed igniting tiny pellets of deuterium and helium-3 using powerful electron beams, creating controlled fusion explosions at a rate of about 250 per second. The design called for a 2-stage spacecraft with a total mass of roughly 54,000 tons at launch, carrying about 46,000 tons of fusion fuel in the first stage and 4,000 tons in the second. This spacecraft was never intended to carry humans. It was designed as an unmanned flyby probe targeting Barnard's star, about 6 light-years away. With a projected travel time of 50 years and a cruise speed of around 12% of the speed of light, it would not slow down when it arrived. It would pass through the system at about 36,000 kilometers per second, collecting data for a brief moment before continuing into deep space forever. 2 aspects of Daedalus reveal the true scale of the challenge. First, It required helium-3 as a fusion fuel, a material so rare on Earth that the entire global supply would barely fill a small room. The designers proposed extracting it from the atmosphere of Jupiter using massive floating platforms, an undertaking that itself would require technologies and infrastructure we do not yet possess. Second, even this extraordinary machine, consuming 50,000 tons of advanced fusion fuel, could only perform a flyby. It had no ability to slow down, enter orbit, or carry out long-term observation. It was essentially a projectile aimed at the stars, incredibly fast, incredibly expensive, and unable to stop. And that brings us to one of the most underestimated challenges in interstellar travel: deceleration. Most discussions focus on how to go faster, but speed is only half of the journey. If the goal is to reach another star system and do anything meaningful, whether that means entering orbit, studying a planet closely, or delivering a human crew, then the spacecraft must also slow down. And reducing speed from a significant fraction of light speed requires almost the same amount of energy as accelerating in the first place. For a rocket-driven spacecraft, this effectively doubles the fuel requirement. You need fuel to speed up, fuel to slow down, and fuel to carry all of that fuel. The exponential nature of the rocket equation becomes unforgiving. A ship that might require 50,000 tons of fuel for a one-way flyby could require several 100,000 tons for a mission that includes deceleration. The spacecraft grows larger, the fuel requirement increases even faster, and the engineering complexity grows faster still. Various alternative braking concepts have been proposed, including magnetic sails that interact with the interstellar medium to create drag, and photon-based braking that relies on starlight at the destination. But each of these ideas carries serious limitations, which become clearer when we look closely at what it actually means to arrive at another star system. For now, the key point is simple: there is no proven method to slow down a large interstellar spacecraft, and any approach that depends on carrying fuel on board will effectively double an already enormous energy requirement. Fusion propulsion, often described as the next step beyond fission, is usually presented as the most promising path toward practical interstellar travel. Fusion reaction, the same process that powers the sun, release roughly 3 to 4 times more energy per kilogram than fission, while producing far less radioactive waste. In theory, a fusion-powered spacecraft could reach exhaust velocities between 10,000 and 30,000 kilometers per second, depending on the design and reaction used. At the upper end of that range, travel times to Proxima Centauri might fall within a few decades for a flyby, and perhaps within a century for a mission that includes slowing down. Concepts such as magnetic fusion plasma drives, along with related designs, have been explored in research as possible architectures for interstellar propulsion, combining magnetic confinement with direct thrust. But the reality is more difficult. Controlled fusion remains one of the most challenging engineering problems on Earth. As of 2026, no fusion reactor anywhere has achieved sustained net energy output. The ITER experimental reactor in southern France, the largest fusion project ever undertaken, has faced repeated delays and rising costs, with its deuterium-tritium experiments now expected no earlier than 2039 under the latest schedule. ITER itself is a massive, ground-based facility, comparable in size to a large industrial building. Supported by the combined efforts of 35 nations, turning controlled fusion from such a vast installation into a compact, lightweight engine capable of operating in space for decades without maintenance represents an engineering leap so large that no realistic timeline can yet be defined. Fusion propulsion is not something we are gradually improving. It is something we have not truly built. The gap between a ground-based fusion reactor and a functional spacecraft engine deserves far more attention because it is often overlooked in simplified discussions that assume once fusion works on Earth, it can easily be adapted for space. In reality, the two challenges are connected but fundamentally different. The most advanced fusion systems on Earth are tokamak reactors, which use superconducting magnets cooled close to absolute zero to contain plasma made of deuterium and tritium at temperatures exceeding 150 million degrees Celsius. The reactor alone can weigh tens of thousands of tons. Its central vacuum chamber stands more than 11 meters tall and nearly 20 meters wide, enclosed within a cryostat almost 30 meters across. It requires external power in the range of hundreds of megawatts just to operate its magnetic fields and heating systems. Around it are cooling systems, diagnostic equipment, and support structures that together occupy an area comparable to a small town. This type of reactor is designed to demonstrate that fusion can produce more energy than it consumes. It is not designed to generate thrust. It produces heat, which on Earth would be used to boil water and spin turbines. A fusion rocket must do something entirely different. It must convert fusion energy directly into directed motion, ejecting particles at extremely high speeds through a nozzle or magnetic structure that channels plasma in a single direction. This introduces a new set of challenges involving plasma behavior, magnetic confinement, structural geometry, materials that can survive extreme conditions, and the management of heat in space. These are very different from the challenges of sustaining a fusion reaction in a stationary laboratory. A space-capable fusion engine must be compact enough to fit within a spacecraft, light enough to be accelerated without requiring impossible amounts of fuel, and durable enough to operate continuously or in repeated high-performance cycles for many years without maintenance. It must also handle the intense neutron radiation produced during fusion, which gradually damages structural material. Even though those components cannot be replaced during the journey, at the same time, it must contain plasma hotter than the core of the Sun within a magnetic structure that cannot fail. Because if that containment breaks, the plasma would instantly destroy the engine itself, and it must accomplish all of this in the vacuum of space, where excess heat cannot be carried away by air or fluid, but must instead be radiated into the void. That requires vast radiator surfaces, adding both mass and structural complexity to the spacecraft. Every step from a laboratory experiment to a working flight system is not simply a matter of scaling up. It requires rethinking and redesigning almost everything from the ground up. The history of aerospace engineering is filled with propulsion ideas that worked in theory, worked in controlled experiment, and then required decades of refinement before becoming practical. Jet engines took around 20 years to move from early demonstrations to reliable use in military aircraft. Liquid-fueled rockets required roughly 30 years from the first experimental launches to achieving orbit. Fusion propulsion begins from an even earlier stage. It starts from a point where sustained net energy production has not yet been achieved. Its development path is therefore likely to be longer and far more uncertain than either of those earlier technologies. At the far end of theoretical possibilities lies antimatter propulsion. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy. This represents the highest energy density allowed by physics, roughly 300 times greater than fusion for the same amount of mass. In theory, a spacecraft carrying only a few hundred grams of antimatter could generate enough energy to reach a significant fraction of the speed of light. In reality, the challenges are almost beyond imagination. First, the total amount of antimatter humanity has ever produced across all particle accelerators is only about 20 nanograms, a nanogram being 1/1,000,000th of a gram. Producing even a few grams would require facilities thousands of times larger than anything we have today, operating for years at energy costs that exceed the output of entire national power systems. Second, antimatter cannot come into contact with normal matter. Even the smallest touch results in immediate annihilation. Scientists have managed to store charged antiparticles in magnetic traps for extended periods in laboratory conditions. Experiments at CERN have even held tens of thousands of antihydrogen atoms at once, but these quantities remain unimaginably small, measured in trillionths of a gram. Storing even a few grams inside a spacecraft, in a container that could survive launch forces, radiation exposure, and long-term thermal cycling, is far beyond any technology we currently possess or can realistically predict. And third, even if production and storage were solved, using antimatter for propulsion presents its own difficulties. When matter and antimatter annihilate, much of the energy is released as gamma rays and neutrinos. Neutrinos pass through matter almost without interaction, carrying energy away that cannot be used. Gamma rays are extremely penetrating and require heavy shielding to protect both the spacecraft and its crew. Some estimates suggest that only about 40% of the total energy could be captured and directed into useful thrust. The remaining 60% would become waste heat and radiation that must be managed or simply endured. Even with the highest possible energy density, real-world engineering limits would significantly reduce performance. Then there is another idea that has attracted widespread attention in recent years. Breakthrough Starshot proposed a completely different approach. Instead of carrying fuel, the spacecraft would be accelerated by a powerful laser system based on Earth. A large array of synchronized lasers, combining to produce around 100 gigawatts of directed energy, would focus a beam onto a reflective light sail about 4 meters across. Attached to that sail would be a tiny payload, often called a starship. The pressure from the light itself would accelerate the sail to about 20% of the speed of light in roughly 10 minutes, exposing it to accelerations tens of thousands of times stronger than Earth's gravity. At that speed, the spacecraft could reach Proxima Centauri in about 21 years. When it finally arrives, the craft would sweep past the system at about 60,000 kilometers per second, gathering data during an encounter that lasts only a few hours before continuing out into deep interstellar space. Breakthrough Starshot was elegant because of its simplicity. By keeping the energy source on Earth, it removed the need to carry fuel. By shrinking the payload to an extreme minimum, it reduced the energy required to reach relativistic speeds, and by completely abandoning any attempt to slow down, it avoided the enormous energy cost of deceleration. The concept reduces the interstellar problem to its bare essence. Send something, anything, as fast as possible. But there is a trade-off. It will never stop. Even this stripped-down version turned out to be extraordinarily difficult. The laser array would need to generate about 100 gigawatts of perfectly synchronized power, comparable to the combined output of roughly 100 large nuclear power plants, focused into a beam precise enough to strike a sail only 4 meters wide from distances of millions of kilometers. Laboratory experiments have demonstrated phase locking with a small number of lasers, but scaling that to millions of laser units operating in perfect synchronization presents an engineering challenge with no clear path forward. The sail material itself must survive intense energy without vaporizing, reflects nearly all incoming light, weigh only a few grams across a 4-meter surface, and remain stable under accelerations that would destroy any known material. Research teams at Caltech and elsewhere have explored ultra-thin membranes made from silicon nitride, producing small experimental samples, but a full-scale sail has never been built. The spacecraft itself would need to carry a camera, a power source, navigation systems, and a communication system capable of transmitting data across 4.24 light-years, all within a mass limit of just a few grams. By September 2025, reports indicated that the project had been placed on indefinite hold after spending only a small fraction of its original $100 million budget. Nearly a decade of work had improved understanding of individual components, but had not produced a complete working system or a clear timeline for construction. The difficulties were not due to a lack of imagination. They were the result of confronting engineering limits at a scale that even $100 million could not begin to solve. Estimates suggest that a full mission could cost between $5 and $10 billion, and even that assumes breakthroughs in laser technology, sail materials, and ultra-light spacecraft design that have not yet happened. And it is important to be clear about what Breakthrough Starshot actually represents. It is not a human mission. It is the smallest, lightest, fastest possible attempt to reach another star. A gram-scale probe on a one-way flyby, no life support, No shielding, no air, no water, no crew, no way to slow down, no way to return. Just a tiny device with a camera, passing the nearest star at 1/5 the speed of light. It would capture only a handful of images during a flyby so brief that the entire Alpha Centauri system would pass through its view in just a few hours. And even that minimal version has proven too difficult so far. It is the simplest possible mission, and it has already stalled, with even the most optimistic projections placing it decades into the future. A human mission to Proxima Centauri is something far beyond this. It requires everything, and then far more. It requires a spacecraft large enough to sustain human life for decades. It requires propulsion capable of accelerating that massive structure, not a gram scale, to a meaningful fraction of the speed of light. It requires energy, whether carried on board or delivered externally, sufficient to both accelerate and slow down. It requires protection against radiation, resilience against impacts with interstellar dust at extreme speeds, and redundancy in every critical system. And it requires all of these systems to operate flawlessly for longer than any machine humanity has ever kept running without interruption. Let us be generous with the assumptions. Imagine that fusion propulsion becomes practical within the next 50 to 100 years. Imagine a fusion engine capable of reaching an exhaust velocity of about 15,000 kilometers per second, roughly 5% of the speed of light. And imagine a spacecraft designed with a mass ratio that allows it to cruise at 10% of light speed while still carrying enough fuel to slow down at its destination at 10% of light speed. The journey to Proxima Centauri would take about 42 years. Add in the time needed for acceleration and deceleration, which could last months or even years depending on how the engine operates. And the total mission stretches to roughly 45 to 50 years. This is the optimistic case, built on technologies that do not yet exist. Assuming that engineering challenges never solved before will somehow be overcome within the next century. Now consider a more cautious, though still ambitious, scenario. Nuclear pulse propulsion, one of the most physically grounded high-performance concepts, might achieve a cruise speed of about 5% of light speed. At that rate, the journey alone takes around 85 years, including acceleration and braking phases. The mission extends to roughly 90 to 100 years. This is no longer a single lifetime. It becomes a journey across generations. The people who arrive would not be the same people who left. Their children might not live to see the destination. Perhaps their grandchildren would. If the cruise speed drops to 3% of light speed, which some studies suggest is more realistic for a large spacecraft, the travel time exceeds 140 years. At 1% of light speed, still about 3,000 kilometers per second and far beyond anything we can achieve today. The journey would take more than 420 years. Each of these estimates assumes everything works perfectly. Continuous propulsion without failure. Precise navigation over decades. A spacecraft that does not degrade beyond repair over time spans longer than most nations have existed. Each assumes that the problem of slowing down has been solved. Each assumes that sufficient fuel can be carried or somehow obtained along the way. And each assumes that such a mission could be funded, built, and maintained by institutions willing to commit resources over many decades or even centuries. And all of these projections apply only to Proxima Centauri, the nearest possible destination. Every other star is farther. Most are far beyond comparison. If reaching the closest one is already this difficult, then the rest of the galaxy remains effectively out of reach. There is a concept in interstellar mission planning known as the weight calculation. First described by researcher Andrew Kennedy in 2006, it addresses a paradox that appears in nearly every proposed mission. If you launch today using the best available technology, a faster spacecraft built decades later could overtake you and arrive first. This leads to a strange conclusion. The rational strategy might always be to wait for better technology before launching, but if you follow that logic indefinitely, you never launch at all. Because there is always the possibility that a future system will be faster, The weight calculation attempts to find the optimal moment to depart, balancing current capability against expected technological progress. Kennedy's analysis suggests that, under realistic assumptions, the best departure time for a mission to Proxima Centauri lies somewhere between several decades and about a century in the future. The exact timing depends on how quickly propulsion technology improves. This idea is not an argument for giving up. It is a mathematical reflection of how difficult the problem truly is. It shows that interstellar travel is not only about building faster engines, it is also about understanding the pace of technological change, the cost of committing too early, and the risk of waiting too long. A civilization that launches too soon may invest everything in a mission that becomes outdated before it arrives. A civilization that delays indefinitely may never launch at all, held back by the constant promise of something better just beyond reach. This perspective reveals something deeper than the numbers alone. The challenge of interstellar distance is not a single problem with a single solution. It is a system of interconnected limits, stretching across physics, engineering, time, and decision-making. It is not a single obstacle, but a system-level challenge shaped by the interaction between physics, engineering capability, institutional commitment, and time itself. Solving it does not only require a faster engine, it demands an entire civilizational foundation, energy production on scales we have never reached, materials we have not yet learned to build, manufacturing systems that do not exist, mission designs that have never been tested, and a level of political and economic commitment sustained across timeframes longer than most human institutions have ever endured. Even today, we struggle to maintain funding for major space projects over just a few decades. The James Webb Space Telescope required about 25 years from concept to launch. The International Space Station has been continuously inhabited since the year 2000, yet it depends on constant resupply from Earth and is expected to operate for only around 30 years. As remarkable as these achievements are, they are still far from the level of long-term commitment an interstellar mission would demand. Now imagine, despite all of this, that we solve the problem of speed. Imagine that a century from now, fusion propulsion becomes mature, that laser sail systems can accelerate large spacecraft, or that some combination of technologies allows us to send a human vessel toward Proxima Centauri at 10% of the speed of light, with the ability to slow down upon arrival. Even then, the journey would still take more than 4 decades in each direction. Communication with Earth would involve a round-trip delay of nearly 9 years. The crew would be completely isolated, farther from home than any human has ever been. They would carry with them everything required to survive for half a century inside a spacecraft that cannot be resupplied, cannot be repaired from Earth, and cannot be rescued. And this is where the discussion moves beyond physics and engineering into something deeper. Because speed was never the only challenge, it is simply the most visible one, the one that produces dramatic numbers and inspires bold ideas. But even if speed is solved, another category of problems remains. Problems that cannot be solved with more powerful engines or stronger lasers. Problems rooted not in distance, but in the limits of the human body, the fragility of the human mind, and the finite reliability of every machine we have ever built. The propulsion challenge is immense, and it may take a century or more to overcome, but it is, in principle, a problem of energy and engineering. The next challenge is different. It is about biology, endurance, and a difficult truth. Keeping human beings alive for decades inside a closed spacecraft, drifting between stars, may be even harder than sending them there. A gram-scale probe does not eat, it does not breathe. It does not develop cancer from cosmic radiation. It does not lose bone density, suffer muscle degradation, or experience cardiovascular decline. It does not feel loneliness, anxiety, or the quiet psychological weight of knowing that everyone it has ever known is aging and fading away 4 light years behind it. It does not require water recycling, carbon dioxide removal, waste processing, temperature control, or emergency medical systems. It does not panic when something breaks. It does not mourn the loss of a companion. It does not need to raise children, resolve conflicts, or maintain a functioning society over decades of confinement inside a sealed structure, moving through the emptiest environment we know. This is the true difference between a robotic mission and a human journey to Proxima Centauri. It is not simply a matter of degree. It is a fundamentally different kind of challenge, and it may prove to be an even greater barrier than propulsion itself. Begin with radiation. Interstellar space is filled with galactic cosmic rays, high-energy particles produced by supernova explosions, active galactic nuclei, and other violent events scattered across the Milky Way. These particles, mostly protons and heavier atomic nuclei, travel at significant fractions of the speed of light and carry enormous energy. When they pass through living tissue, they do not simply pass through harmlessly. They ionize atoms along their path, breaking molecular bonds, damaging DNA, and triggering cascades of secondary particles that spread the damage further into surrounding cells. Here on Earth, we are protected. The planet's magnetic field and atmosphere shield us from much of this radiation. The total natural background radiation from all sources, including cosmic rays, terrestrial radioactivity, radon gas, and radioactive elements within the body, averages about 2.4 millisieverts per year. In low Earth orbit, aboard the International Space Station, astronauts receive far higher exposure, roughly 160 to 320 millisieverts per year, depending on solar activity. Even there, Earth's magnetic field still provides partial protection by deflecting many incoming particles. And yet, even this reduced level is already tens of times higher than what we experience on the ground. Out in interstellar space, beyond any planetary magnetic field, that protection disappears completely. The full intensity of cosmic radiation reaches the spacecraft, delivering an estimated dose of about 400 to 600 millisieverts per year. Depending on variations in solar activity, over a 40-year journey to Proxima Centauri at 10% of the speed of light, a crew member would accumulate a total radiation dose of roughly 16 to 24 sieverts. To understand what that means, a single whole-body dose of 5 sieverts is considered lethal to about half of exposed individuals without medical treatment. A dose of 20 sieverts delivered all at once would be fatal within days. In interstellar travel, the exposure is not sudden, but spread out over decades. This allows the body some ability to repair damage, but even so, long-term exposure at these levels dramatically increases the risk of cancer, potentially by several 100% above normal levels. Studies of atomic bomb survivors and radiation workers have consistently shown that cumulative doses above 1 sievert significantly raise the likelihood of leukemia, solid tumors, cardiovascular disease, and cataracts. At higher levels, radiation also begins to affect the brain. Damage to regions such as the hippocampus and prefrontal cortex can impair memory, decision-making, and cognitive function. NASA currently limits astronaut careers to radiation exposures that correspond to no more than a 3% increase in lifetime fatal cancer risk. Under current standards, this translates to a lifetime limit of about 600 millisievert. A single interstellar mission lasting 40 years would exceed that limit by 20 to 40 times. Research conducted by NASA, including experiments on the International Space Station and studies using animal models at Brookhaven National Laboratory, has shown that prolonged exposure to heavy ion radiation, one of the most damaging components of cosmic rays, can lead to persistent inflammation in the brain, accelerated aging, and behavioral changes with no known treatment. Shielding against this type of radiation is far more complex than shielding against solar radiation or medical X-rays. Lower energy radiation can be blocked by relatively thin layers of dense materials such as lead or aluminum. But galactic cosmic rays carry so much energy that when they collide with dense shielding, they create showers of secondary particles, including neutrons and pions, which can be even more harmful than the original radiation. This process, known as secondary particle production, means that adding conventional shielding can sometimes make the situation worse rather than better. The most effective shielding materials against galactic cosmic rays are substances rich in hydrogen, such as water or polyethylene. Hydrogen nuclei can absorb energy from incoming particles without generating as many dangerous secondary fragments. But effective protection requires thickness. Studies by NASA researchers suggest that reducing the radiation dose by about half would require roughly 20 to 30 centimeters of water, equivalent shielding surrounding the entire living space of the spacecraft. For a habitat with an internal volume similar to the pressurized sections of the International Space Station, around 900 cubic meters, the shielding mass alone could reach into the hundreds of tons. And every additional ton increases the energy needed to accelerate and slow the spacecraft, intensifying the propulsion challenge we have already seen. For a mission already operating at the edge of what seems physically possible, adding hundreds of tons of shielding may simply be beyond any realistic mass limit. Some ideas have proposed using electromagnetic fields to deflect charged particles, mimicking Earth's magnetic protection. Concepts involving superconducting magnetic shields have been explored in theory, but generating a field strong enough to deflect the most energetic cosmic rays, particles with energies reaching billions of electron volts, would require magnetic field strengths and structures far beyond what current technology can produce. These magnetic systems would also add considerable mass and would need continuous power to maintain temperatures near absolute zero throughout the entire mission. No working prototype exists, and no engineering study has yet demonstrated that such a system could be built for a spacecraft. The radiation problem does not have a practical solution. What exists instead are theoretical ideas, each carrying trade-offs so severe that they threaten the feasibility of the mission itself. Now consider life support. The International Space Station, the most advanced closed living environment ever constructed, typically supports a crew of 6 to 7 people in low Earth orbit. It recycles part of its water and oxygen, but still depends heavily on frequent resupply missions from Earth. Each year, roughly 8 to 12 cargo missions deliver food, spare parts, filters, clothing, scientific equipment, and other essential supplies. The station's life support system has recently achieved the ability to recover about 98% of water from humidity, urine, and other sources, a milestone reached in 2023 with the addition of advanced processing systems. But even that remaining 2% must still be replaced from Earth. Oxygen is mainly produced by splitting water through electrolysis, supported by additional supplies delivered from cargo vehicles. Carbon dioxide is removed using regenerative filtration systems, which have experienced repeated failures over time and require replacement parts sent from Earth. None of these systems operate indefinitely without maintenance. Pumps fail, filters become clogged, seals wear out, and sensors drift from calibration. On the International Space Station, astronauts spend a significant portion of their time performing repairs and upkeep. They rely on a continuous supply of replacement components delivered from Earth. They can also communicate with engineers on the ground almost instantly, with delays of only about 1 second. And, if something goes seriously wrong, evacuation is possible within hours using dock spacecraft such as Soyuz or Crew Dragon. An interstellar spacecraft would have none of these safeguards. There would be no resupply missions, no spare parts arriving from Earth. Communication with mission control would involve delays of years, making real-time problem-solving impossible. A message sent from a ship halfway to Proxima Centauri would take more than 2 years to reach Earth, and any reply would take just as long to return. By the time a response finally arrives, the situation that triggered the question has already resolved itself. One way or another, for nearly 4 years, there is no possibility of evacuation. If the spacecraft suffers a critical failure, the crew cannot return to Earth, and they cannot divert to another destination. They are alone in interstellar space with only what they brought and whatever they can manage to create from it. This reality demands life support systems that function in a completely closed loop, recycling all water, all oxygen, and ideally producing food without any external supply for the entire mission. No such system has ever been successfully built. The closest attempt was Biosphere 2, a sealed ecological experiment constructed in Arizona in the early 1990s, designed to support 8 people in a self-contained environment. The project encountered major problems almost immediately. Oxygen levels dropped to dangerous levels and required external intervention. Carbon dioxide fluctuated unpredictably. Many plant and animal species introduced into the system failed to survive. Insect populations collapsed, disrupting pollination and reducing food production. The crew faced significant food shortages and increasing interpersonal tension. Biosphere 2 demonstrated that building a fully self-sustaining ecosystem, even on Earth, with constant sunlight and the option to exit at any time, is extraordinarily difficult. It remains the most ambitious attempt ever conducted. And it did not achieve complete self-sufficiency. Growing food in space introduces even greater complexity. Experiments aboard the International Space Station have successfully produced small amounts of lettuce, radishes, and peppers in controlled environments. These results show that plants can grow in microgravity and can produce edible food, but these experiments are far from proving that a crew can be sustained this way. Producing enough food to support even a small group requires large growing areas, stable lighting systems, precise water and nutrient control, protection from pests, and reliable harvesting processes. Estimates suggest that space agriculture capable of supporting a crew would require hundreds to over 1,000 square meters of cultivation area, operating continuously without failure. On Earth, a poor growing season might mean higher prices or limited supply. On an interstellar spacecraft, a failed harvest could mean starvation. Medical care adds another layer of difficulty. On the International Space Station, astronauts have access to basic medical equipment, can consult doctors on Earth almost instantly, and can return home within hours in an emergency. None of these options exist on an interstellar mission. The onboard medical team, if one exists, must be prepared to handle every possible condition across a population of dozens or even hundreds of people over a period of 40 years or more. This includes injuries from accidents, mechanical failures, or maintenance work, as well as surgical emergencies such as appendicitis or intestinal blockages. It also includes heart attack, strokes, dental infections that can become life-threatening if untreated, kidney stones, broken bones, burns, and the full range of chronic diseases that naturally develop over time, including diabetes, high blood pressure, autoimmune conditions, and cancer. Performing surgery in space presents its own challenges. In microgravity, blood does not flow downward. It forms floating droplets that obscure vision and can contaminate the cabin environment. Bodily fluids drift freely, and instruments must be carefully secured. The patient must be held in place, since there is no gravity to keep them stable. Even if artificial gravity is created by rotating the spacecraft, the resulting Coriolis effects can cause disorientation and nausea, making precise surgical work more difficult. Current research into space-based surgery is still limited to animal studies and simulations. No human surgical procedure has ever been performed in space. The equipment required for a fully functional medical facility, including sterilization systems, anesthesia delivery, blood storage, and recovery areas, would add significant weight and complexity to the spacecraft. Infectious disease becomes an especially dangerous threat inside a sealed environment. The crew lives within a closed atmospheric loop. Any pathogen that enters the system remains inside it. On Earth, outbreaks are partly controlled by distance, quarantine, and the vast volume of open air that helps dilute airborne particles. Inside a spacecraft with a fixed atmosphere shared by everyone on board, a new respiratory illness could spread through the entire crew within days. Bacteria that develop resistance to antibiotics, something that happens more easily in closed environments where medications are used repeatedly, could make the ship's limited medical supplies ineffective against even common infections. Research from the International Space Station has shown that microgravity may increase the virulence of certain bacteria while also weakening parts of the human immune system. A crew living for decades in a sealed spacecraft would face the constant risk of an outbreak that could disable a large portion of the population at the same time. With no external medical help, no evacuation, and only a finite supply of treatments, the inability to evacuate changes everything. On Earth, and even on the International Space Station, there is always an alternative. If a patient cannot be treated locally, they can be transported to a better equipped facility. On an interstellar mission, the spacecraft is the only facility that exists. If a crew member develops a condition beyond what can be treated on board, the outcome depends entirely on what equipment is available and what the medical team can improvise. There is no rescue, no ambulance, no hospital waiting nearby. Every limitation in the medical system becomes a possible point of failure for conditions that would normally be manageable on Earth. The question of crew size adds another layer of complexity. A larger crew offers clear advantages, more people available for maintenance and repairs, a wider range of skills, greater genetic diversity for long-term survival, and stronger psychological stability through social interaction. But a larger crew also requires more of everything: more food, more water, more oxygen, more living space, and more medical resources. Every system must scale up. A smaller crew reduces resource demands, but increases risk. If a key individual becomes incapacitated, the only physician, the only engineer capable of maintaining the propulsion system, or the only person who fully understands navigation, the entire mission could be compromised, even if every other system continues to function perfectly. To ensure redundancy in knowledge and skills, you need more people. More people require a larger spacecraft. A larger spacecraft demands more propulsion. The cycle reinforces itself at every level. Then there is the question of mechanical reliability over timescales that extend far beyond anything we have ever built. The longest operating human-made systems in space are the Voyager probes, which have remained functional for nearly 50 years. They are incredibly durable, but also extremely simple compared to what an interstellar vessel would require. Voyager has no complex moving systems in its main structure. It does not support life. Its instruments use very small amounts of power from radioisotope generators that slowly weaken over time. Several of its instruments have already failed. Its power output declines year after year, and mission controllers have gradually shut down systems to preserve what remains. By the middle of the 2030s, Voyager will likely no longer have enough power to operate its instruments at all. An interstellar spacecraft is not a simple probe drifting silently through space. It is something far more complex. It is a self-contained world, a small city sealed inside a machine, carrying human life across the vast distance between stars. It contains pumps, valves, compressors, heat exchangers, electrical distribution network, computer systems, atmospheric controls, water purification units, food production systems, medical facilities, communication arrays, navigation instruments, structural monitoring systems, and a propulsion system that must restart flawlessly after decades of inactivity for the final deceleration. Each of these systems includes parts that slowly wear down, corrode, fatigue, or degrade over time. Seals become brittle and crack. Bearings wear out. Solder joints develop tiny fractures from repeated thermal expansion and contraction. Electronic circuits accumulate radiation damage that alters how they behave. Lubricants can evaporate or break down chemically. Nothing is truly permanent, and an interstellar mission demands that everything lasts for an extremely long time. On Earth, engineering deals with failure through maintenance, inspection, and replacement. Vehicles are serviced regularly. Power plants shut down for overhaul. Aircraft are inspected after every flight, with critical components replaced long before they fail. All of this depends on supply chains, factories, and skilled workers producing replacement parts. None of that exists on a spacecraft traveling between stars. Every spare part must either be carried from the beginning or produced during the journey. Carrying replacements for every possible failure over a mission lasting 40 to 100 years quickly becomes impractical due to mass limit. Manufacturing parts during the journey introduces its own challenges. It requires machine tools, raw materials, and production systems, all of which add more weight and complexity. Three-dimensional printing offers some potential, but current technology can only produce relatively simple components using a limited range of materials. Creating something like a circuit board, a precision bearing, or a high-pressure seal requires capabilities far beyond what current in-space manufacturing can achieve. And in space, conditions such as microgravity, limited power, and restricted material supplies make the problem even harder. Even optimistic forecasts for future manufacturing in space do not suggest the ability to produce complex, highly reliable components comparable to those made on Earth, at least not within the timeframes relevant to interstellar missions. The failure of a single critical system, one without a backup or repair option, could end the mission, not in a sudden explosion, but in a slow and irreversible decline. The crew might watch their air filtration systems lose efficiency, their water recycling degrade, or their food production gradually fail. As essential components break down one by one, the spacecraft would not fail dramatically. It would simply become less and less habitable over time. The margin between survival and death would shrink with each part that could not be replaced. And over decades, many components will inevitably reach the end of their useful life. Beyond engineering, there is another challenge that is just as serious. Human psychology under extreme isolation and confinement. It is often treated as a secondary concern, but it may be just as critical as any technical problem. Studies of crews in Antarctic stations, long submarine deployments, and simulated missions such as the Mars 500 experiment, where 6 people lived in isolation for over 500 days, consistently show the psychological strain caused by long-term confinement. These effects include depression, anxiety, interpersonal tension, disrupted sleep patterns, reduced cognitive performance, and a gradual loss of motivation. In the Mars 500 experiment, several participants became more sedentary over time, experienced irregular sleep cycles, and showed measurable declines in alertness and mental performance as the simulation progressed. And that experiment lasted only 520 days, less than 2 years, with the constant reassurance that it would eventually end and normal life would return. An interstellar mission offers no such comfort. The crew departs knowing they will not come back to Earth for decades. If they return at all, communication with family and friends becomes increasingly distant, as light-speed delays stretch from minutes to hours, and eventually to years. The sense of connection to Earth slowly fades. The idea that help is available, that someone is watching, that return is possible, gradually disappears as the ship moves deeper into interstellar space. After a few years, the crew exists in a kind of communicative silence. Messages from Earth arrive long after they were sent, describing people and events that have already changed beyond recognition. In the time between messages, the crew cannot take part in life on Earth. They can only observe delayed fragments of it, distant and increasingly irrelevant. The behavior of small groups living in confined environments for long periods is still not fully understood and remains difficult to predict. Studies from Antarctic bases and submarine crews show that even highly trained individuals can develop friction, conflict, and experience conflicts that sometimes escalate into serious problems. For shorter missions, these tensions can be managed, but extend the duration to decades. Remove any possibility of rotation. Outside mediation, or personnel change, and the psychological strain becomes something entirely different. There is no real data for how human groups behave in sealed environments over 10, 20, or 40 years. We are making assumptions, and the cost of being wrong could be fatal. The question of governance on a multi-decade interstellar mission is rarely discussed. yet it may be just as critical as any engineering challenge. Every human society depends on systems of authority, decision-making, conflict resolution, and resource distribution. On Earth, these systems develop over long periods, supported by culture, laws, institutions, and the simple fact that individuals can leave if they choose. On an interstellar spacecraft, no one can leave. The community is closed, permanent, and unavoidable. Whatever structure is established at departure must remain functional for decades without the stabilizing influences that exist on Earth. Who controls the ship? A strict hierarchical model, similar to a military structure, offers clear authority and fast decisions. But over long periods it risks becoming rigid or oppressive, especially without external oversight. A more democratic system allows broader participation, but introduces the risk of division, deadlock, or majority dominance in a confined group where dissenting individuals have nowhere else to go. Hybrid systems attempt to balance these approaches, but they face the challenge of defining boundaries between technical authority and social governance in an environment where nearly every decision, from food allocation to reproduction to daily work, can have life or death consequences. Leadership succession introduces another layer of instability. A mission lasting 40 to 100 years will inevitably outlast the original leadership. The first commander may die, become incapacitated, or simply grow too old to continue. Transferring authority in an isolated, closed system without external arbitration is historically one of the most dangerous moments any society can face. Mutinies at sea, conflicts in isolated settlements, and political crises in closed systems all demonstrate how unstable these transitions can become. On an interstellar spacecraft, such a crisis does not only threaten social order, it threatens survival itself, because the operation of the ship depends on coordinated technical control that can break down if governance fails. And beyond all of this lies an even deeper question, the question of purpose. The original crew leaves Earth with a shared mission. They made the decision to go. They understood the risks. Their commitment was voluntary and fully informed. But what about their children? What about the crew members who, 20 years into the journey, begin to wonder whether the mission is still worth the cost? On Earth, when people lose belief in an institution, they can step away, move somewhere else, or choose a different path. On an interstellar spacecraft, there is no exit. A crew member who no longer believes in the mission must still continue their duties because the survival of everyone depends on collective effort. Being required to work in support of a mission one did not choose and may no longer believe in raises ethical questions that cannot be fully resolved through training or selection before departure. As the years pass, the shared sense of purpose may begin to weaken, and as it fragments, the ability of the community to hold itself together without force becomes more fragile. Incidents aboard the International Space Station offer small glimpses of what such a future might look like without support from Earth. In 2020, a minor air leak was discovered in the Zvezda module, caused by small cracks in a section that had been in orbit for 2 decades. The crew spent months tracking down the source before finally sealing it with materials available on board. If the leak had been larger or harder to reach, the outcome could have been far more serious. In 2007, a failure in the station's computer systems disrupted both attitude control and oxygen generation at the same time. The crew depended on backup systems and emergency procedures, while engineers on Earth worked to diagnose the issue over several days. In late 2013, a coolant pump failed in one of the station's external systems, requiring complex spacewalks to replace it, using spare parts that had already been delivered. In each case, success depended on 3 critical supports: immediate communication with experts on Earth, access to replacement hardware delivered from the ground, and the option to delay or manage the problem until help arrived. Remove all 3, and each of these situations could have ended the mission. An interstellar spacecraft would have none of these advantages. It would not be a station that can be gradually repaired with outside support. It would be a closed system, where every failure must be handled using only what is already on board. The crew may not include a specialist for every system, and the necessary spare parts may not exist. Meanwhile, the engineers who designed the ship are 4 light-years away, with communication delays stretching across years. The idea of a generation ship attempts to address the problem of time by accepting that no single crew will complete the journey. Instead, an entire community would live and evolve aboard the vessel across multiple generations. Children would be born, grow up, and eventually reach the destination. This removes the need for any one individual to survive the entire trip, but it introduces a new set of challenges. The ship must now support not just a crew, but a functioning society. It must include education, governance, cultural continuity, and enough genetic diversity to sustain a healthy population over time. Birth rates must be carefully managed to match available resources. Studies suggest that a stable, multi-generational population would require at least several hundred and possibly thousands of individuals, depending on how genetics and social systems are managed. A spacecraft carrying that many people would need vastly larger life support systems, more food production, more living space, and far greater resource reserves. The size and complexity of such a vessel go far beyond anything currently considered in serious engineering plans. And beyond the technical challenges, generation ships raise deep ethical questions that remain unresolved. The people who leave Earth make that choice. Their children, born aboard the ship, did not make that choice. They enter a life of confinement from the beginning. They inherit a mission they never agreed to. They grow up inside a system designed for a purpose they may never personally embrace, all to deliver a future generation to a destination the original crew will never witness. Whether it is morally acceptable to create lives under such conditions, lives defined by decisions made generations earlier, with no chance to return to Earth or choose a different path, is a question that philosophy has yet to answer, and one that engineering alone cannot resolve. Suspended animation, or human hibernation, is often suggested as a solution to long-duration space travel. If the crew could enter a state of extremely low metabolic activity for the journey, many challenges — food, water, oxygen, psychological strain, and social conflict — would largely disappear. The crew would effectively sleep through the voyage and awaken near the destination, having aged very little. This idea is common in science fiction and remains an area of scientific curiosity, but it is not a technology that currently exists. No human has ever been placed into suspended animation and later revived successfully. Medical techniques such as therapeutic hypothermia, used after cardiac arrest, reduce body temperature by only a few degrees and are maintained for hours or days, not years or decades. Some animals, including certain ground squirrels, bears, and amphibians, can enter states of torpor or hibernation that dramatically slow their metabolism. Early research has explored whether similar states could be induced in humans, with limited success in animal studies, but the gap between briefly lowering the metabolism of a small animal and placing a human into a controlled dormant state for 40 years remains enormous. There are still unresolved issues at every level: cellular damage during prolonged metabolic suppression, maintaining hydration and nutrition over extended periods, the risk of ice crystal formation in tissues, and severe muscle and bone loss from long-term inactivity. Suspended animation remains a possibility for the future, but not a solution we can rely on today. It belongs to the category of ideas that might exist someday, not to the set of technologies that can guide real mission planning. All of these challenges together create an important distinction that is often overlooked. Sending a small robotic probe past the nearest star is already extremely difficult. It has resisted every serious attempt so far, even those supported by leading scientists and substantial funding. But it is still a problem grounded in known physics and within the reach of future engineering. Sending human beings to the nearest star and keeping them alive for the entire journey is something entirely different. It requires more than propulsion. It requires building a complete, self-sustaining world. Compressed into a spacecraft that must operate flawlessly for decades, in one of the most hostile environments imaginable. It means solving radiation exposure, fully closed life support, long-term mechanical reliability, sustainable food production, comprehensive medical care, psychological endurance, and social stability, all at once, with no room for failure. On Earth, we improve systems through cycles of testing, failure, and redesign. In deep space, there is no second attempt. The first failure may be the last. There is no opportunity to rebuild when the nearest support is trillions of kilometers away. The propulsion challenge asks whether we can build an engine powerful enough to bridge the distance. The human challenge asks whether we can create a system resilient enough to survive the journey. These are not the same problem, and solving one does not solve the other. The human challenge is limited not by physics alone, but by biology, by the endurance of the human body and mind, by the reliability of materials and machines, and by the simple fact that no closed ecosystem supporting human life has ever operated independently for more than a few difficult years. And yet, even after all of this, there is still one final dimension to consider. It is not enough to launch, to endure, and to arrive. The spacecraft must also slow down. And as we are about to see, stopping may demand more from the mission than everything that came before it combined. Now imagine the full mission, not just one part, but every part working together, from the first bolt to the final breath. A spacecraft large enough to house a crew of perhaps 50 to several hundred people, depending on how the mission is designed. Inside it are closed-loop life support systems, food production areas, medical facilities, repair workshops, stores of raw materials, radiation shielding, navigation instruments, communication systems, and multiple layers of redundancy for every critical component, enough to survive decades of failures without any resupply. This vessel would likely weigh somewhere between tens of thousands and hundreds of thousands of tons, depending on crew size, shielding needs, and the propulsion system used. It could not be launched from Earth in one piece. It would have to be assembled in orbit, piece by piece, and that assembly alone would be an engineering effort far larger than the International Space Station, beyond anything humanity has ever attempted in space. Such a project would take decades and require resources on a scale no single nation has ever committed to a space mission. And once complete, this massive structure must be accelerated to a meaningful fraction of the speed of light. At 10% of light speed, one of the most optimistic targets for advanced propulsion, the spacecraft would travel at about 30,000 kilometers per second. Accelerating something of this size to that speed requires energy on a scale that is difficult to grasp. A spacecraft with a mass of 100,000 tons, moving at 10% of the speed of light, would carry kinetic energy of roughly 4.5 times 10 to the 25th joules. For comparison, all of human civilization currently consumes about 5.8 times 10 to the 20th joules of energy per year. That means the energy required just to accelerate the ship would equal roughly 77,000 years of total global energy production. Even if we assume a perfect fusion engine operating at ideal efficiency, the amount of fuel required would still be many times greater than the mass of the ship itself. But let us assume, for the sake of the argument, that this energy challenge is somehow solved, that a fuel source exists, whether carried on board, gathered along the way, or supplied externally, capable of providing the required acceleration. The ship reaches 10% of light speed and enters its cruise phase for about 40 years, perhaps slightly more or less depending on how the mission is planned. It travels through interstellar space. During that time, every system must continue to function. Life support must recycle water, oxygen, and carbon dioxide without any loss. Food systems must produce enough to sustain the crew year after year without failure. Radiation shielding must protect against levels of cosmic exposure far beyond anything humans have experienced. Every mechanical component, Every seal, pump, filter, circuit, bearing, and structural element must either last far beyond its expected lifespan or be replaced using onboard manufacturing systems that do not yet exist. The crew must remain mentally stable through decades of isolation in an environment more extreme than any human society has ever endured. And all of this must succeed on the first attempt. There is no separate test mission. The mission itself is the test. But even reaching the vicinity of Proxima Centauri is not the same as truly arriving there. And that difference, though it may sound small, is where many interstellar mission ideas begin to break down. A spacecraft traveling at 10% of light speed moves at roughly 108 million kilometers per hour. At that speed, the entire planetary system around Proxima Centauri, which spans only a few astronomical units, would be crossed in a matter of hours. If the spacecraft does not slow down, it performs only a flyby. The crew would have a brief window, perhaps a few days in the outer regions, and only hours near Proxima b, to observe the world they spent decades traveling to reach. Then the system would fall behind them, shrinking into the distance at 30,000 kilometers every second. And they would continue into interstellar space, with no destination ahead and no possibility of return. A flyby is not a mission in the human sense. It is only a fleeting glimpse. For a robotic probe, such a moment may still hold scientific value. For a human crew that has spent 40 years crossing the darkness between stars, a simple flyby would feel less like success and more like loss. To truly enter the Proxima Centauri system, to settle into orbit, to observe Proxima b up close, or even attempt a landing, the spacecraft must slow down from 10% of the speed of light to stable orbital speeds. That requires removing nearly all of the kinetic energy built up during acceleration. And the challenge of slowing down is not just the reverse of speeding up. In many ways, it is even more difficult. During acceleration, the spacecraft begins its journey within a well-supported solar system. It can rely on infrastructure, energy sources, early resupply, and near real-time communication. But during deceleration, the situation is completely different. The ship is alone, 4 light-years from Earth, approaching a faint red dwarf star with no supporting systems, no assistance, and no tolerance for failure. Every unit of energy required to slow down must come from the ship itself, or from interactions with the destination environment that remain largely theoretical. If the propulsion system depends on onboard fuel, then that fuel must have been carried for the entire 40-year journey, adding to the mass that had to be accelerated in the first place. The rocket equation makes this especially unforgiving. A spacecraft designed to both accelerate and decelerate must carry exponentially more mass than one performing a simple flyby. A vehicle that might require a mass ratio of 10 for a one-way pass could require a ratio of 100 or more when braking is included. Depending on engine performance, there are alternative ideas. At least in theory, one involves a magnetic sail, a large loop of superconducting material generating a magnetic field that interacts with charged particles in interstellar space or the stellar wind of the destination star. In principle, this interaction could create a form of drag, gradually slowing the spacecraft without using fuel. The physics behind the idea is sound. Charged particles deflected by the magnetic field transfer momentum to the sail, reducing the ship's speed over time. But the force involved is extremely small. Slowing down would take years, and the system would need to operate reliably at the end of a journey where every onboard component has already been running for decades. The sail itself would have to deploy perfectly after 40 years of storage and continuous exposure to radiation. No magnetic sail has ever been built or tested in space at any meaningful scale. Another concept suggests using the light from the destination star as a braking mechanism. For laser sail design, the sail could be adjusted to reflect incoming light, using photon pressure to reduce speed. But this approach is far more practical for tiny probes than for large human spacecraft. Proxima Centauri emits only a tiny fraction of the Sun's energy, and its light pressure is far too weak to significantly slow anything larger than a very small payload. A human-scale spacecraft cannot depend on starlight to bring it to a stop. The star itself is simply too faint. The physics does not scale in a way that helps us. Now consider what the spacecraft actually faces as it begins to slow down. At 10% of the speed of light, even the smallest particles in space become dangerous. A tiny grain of dust, with a mass of about 1 microgram, no larger than a fine speck of sand, carries energy comparable to a small explosive when moving at that speed. The interstellar medium may seem empty, but it contains roughly 1 atom per cubic centimeter on average, along with scattered dust particles. Over a journey of 4.24 light-years, the cumulative effect of these impacts becomes significant. Throughout the cruise phase, the front of the spacecraft must endure a constant stream of high-speed collisions, like an invisible storm of particles. Various protective strategies have been proposed. These include layered shielding that slowly erodes under impact, electromagnetic systems to deflect charged particles, and carefully orienting the spacecraft to reduce exposed surface area. But none of these approaches have been tested under real interstellar conditions. During deceleration, the situation becomes even more complex. The spacecraft may need to rotate or change orientation to fire its engines or deploy braking systems, potentially exposing previously protected areas to the incoming particle stream. The geometry of its shielding changes at the very moment it is most vulnerable. Now add the operational challenge. The propulsion system, whether based on fusion, nuclear pulse concepts, or another advanced design, must restart and perform at full capacity after decades of inactivity or minimal use. No engine in human history has ever been required to do this. Critical components such as turbopumps, injectors, combustion chambers, and fuel systems degrade over time, even under controlled conditions. In the harsh environment of space, exposed to radiation, temperature extremes, and vacuum for 40 years, expecting flawless performance is not cautious engineering. It is hope pushed to its limit. If the braking system underperforms, the spacecraft enters the Proxima Centauri system too fast to establish orbit. If it fails completely, the crew passes through at interstellar speed and continues onward into deep space, with no chance to return. There is no second attempt. There is no rescue. The difference between success and failure depends on whether machines built on Earth, tested only within our solar system, can perform their most critical function after the longest period of dormancy ever required of any engineered system. But assume, against all odds, that everything works. The ship slows down. It enters orbit around Proxima Centauri. The crew, having survived decades of radiation, closed life support, mechanical wear, and psychological isolation, finally arrives and looks upon Proxima Centauri b. What do they find? As of 2026, we do not know. Proxima Centauri b lies within the so-called habitable zone, a region where temperatures might allow liquid water, but this does not guarantee life, or even an atmosphere that humans could breathe. Proxima Centauri is an active flare star, frequently releasing bursts of ultraviolet and X-ray radiation strong enough to strip away a planet's atmosphere over long periods of time. Whether Proxima b has managed to retain an atmosphere depends on factors we cannot yet measure. It may require a strong magnetic field to deflect stellar particles, and an atmosphere thick enough to survive billions of years of exposure. The planet is likely tidally locked, meaning one side constantly faces the star while the other remains in permanent darkness. Although more complex rotational patterns are still possible, conditions on its surface could vary dramatically depending on how heat is distributed. Whether its atmosphere can circulate energy effectively enough to create stable, habitable regions remains an open question, one that current models can only begin to explore. Proxima Centauri b could be a world alive with oceans and shifting weather. It could just as easily be a dry, lifeless rock, stripped bare by relentless stellar radiation, or it might exist somewhere in between. with a narrow, habitable band along the boundary where eternal daylight meets endless night. We simply do not know, and a crew that has spent 40 years reaching it would learn the truth only after committing every resource and leaving behind any chance of turning back. Step back and look at the entire picture. The mission demands orbital construction capabilities that do not yet exist. It requires propulsion systems that have not been built. It calls for energy levels far beyond what any civilization currently produces. It depends on fully closed life support systems that have never been achieved, and radiation protection methods that remain unproven. It also requires machines to operate reliably across time spans. No engineered system has ever reached the human minds to endure conditions never experienced before, and braking systems that must perform flawlessly after decades of dormancy. And all of this effort, all of this risk, is aimed at a destination whose true nature is still unknown, and may ultimately be hostile to human life. This is not a list of reasons why interstellar travel is forbidden. The laws of physics do not prevent it. Nothing in nature stops a spacecraft from crossing the distance between stars. The speed of light is a limit, but not an obstacle at the speeds being considered here. Fusion energy exists. Nuclear processes can provide immense energy. Materials could, in principle, be shaped into the required structures. And human beings, despite their fragility, have shown a remarkable ability to adapt. We have survived in extreme environments, from polar regions to deep oceans, and even in orbit above Earth. None of this is in question. What remains uncertain, and what deserves more honest discussion, is whether the gap between what physics allows and what humanity can realistically build, test, maintain, and commit to over the required timescales can actually be closed. Physics permits the journey. Engineering has not yet made it real, and the gap between those two is not small. It is vast. Not a step to be crossed, but a canyon that may take centuries to bridge. There is a concept in the philosophy of technology that helps clarify this. The difference between something being theoretically possible and something being practically achievable. Many things are possible in theory. It is possible to count every grain of sand on Earth. It is possible to construct a tower reaching into geostationary orbit. It is possible to dismantle a planet and build a vast structure around the sun. None of these ideas violate the laws of physics. But all of them lie so far beyond current capability that calling them possible without qualification becomes misleading. They are possible in the same way that a person could walk from New York to Beijing. The human body can walk. The path exists in principle. But the ocean in between transforms that possibility into something effectively unreachable. The nearest star is our ocean. The path is real. Physics allows the journey, but completing it requires capabilities we do not yet possess, and cannot confidently predict within any near future. We have not returned humans to the surface of the moon since 1972. The Artemis program, designed to restore that capability, has faced years of delays. We have never sent a crew beyond the Earth-Moon system. We have never demonstrated fully closed life support for long durations. We have not yet built a fusion reactor that produces sustained net energy. We have never created a spacecraft capable of reaching even 1% of the speed of light, and we have never tested any true interstellar propulsion system beyond small-scale experiments and simulations. Each of these is a requirement for any true human mission beyond the solar system, and not one of them has been fully achieved. The unsettling reality is not simply that the stars are distant. That has been understood for generations. The deeper truth is that even the nearest star, the closest possible destination, already lies so far beyond our current abilities that even the most optimistic projections place a human mission centuries ahead. We are not close to reaching Proxima Centauri. We are not even close to being close. We are standing at the edge of an ocean we have only just begun to understand. And the opposite shore is so far away that we cannot yet say with certainty whether it could support us at all. This is not a failure of ambition. Human ambition is remarkable. Within a single century, we moved from the first powered flight to landing on the moon. Within one generation, We built telescopes capable of observing the edge of the observable universe, discovered thousands of planets beyond our solar system, detected gravitational waves from merging black holes, and captured the image of a supermassive black hole tens of millions of light-years away. We are a species that looks at the universe and refuses to accept that it is out of reach. That refusal is one of our greatest strengths, but ambition must eventually confront scale. And the scale of interstellar space is unlike anything humanity has ever faced. The distance between the farthest journey ever made by humans, the Apollo missions to the Moon at about 1.3 light-seconds away, and the nearest star at 4.24 light-years is not a gap that can be closed by slightly better rockets. It is a difference of roughly 100 million times. Crossing that distance will require more than incremental progress. It demands transformation at the level of civilization, new physics translated into new forms of engineering, new engineering sustained across entirely new timescales, institutions capable of maintaining focus across generations, solutions to biological and psychological challenges that we are only beginning to understand. Perhaps one day, humanity, or whatever we evolve into, will cross that distance. Fusion propulsion mais mature. New physical principles may open paths we have not yet imagined. Artificial intelligence and autonomous manufacturing might allow spacecraft to repair and rebuild themselves during the journey. Advances in biology could enable the human body to tolerate radiation, survive long periods of dormancy, or adapt to conditions that would be lethal today. None of these possibilities are forbidden, but all of them remain beyond what we can confidently predict. What we can say, based on current knowledge, is clear. The nearest star lies 4.24 light-years away. It hosts a planet roughly the mass of Earth within its habitable zone. These are confirmed observations. But every propulsion system capable of reaching that star within a human lifetime has yet to be built or tested. That is the current state of engineering. And sustaining human life across such a journey would require solutions to radiation exposure, life support, system reliability, and long-term psychological survival that do not yet exist. That is not speculation. It is the reality defined by biology, by engineering, and by the limits of the systems we have built so far. Even the smallest serious attempt at reaching another star, a gram-scale probe on a one-way journey, has already slowed to a halt after years of effort. That is not failure. It is a quiet reminder of how large the challenge truly is. The stars are not forbidden to us, but the nearest one, the faintest point of light just beyond our sun, remains far outside the reach of human travel today. Not by a small margin, not by a gap we can close in a few generations, but by a distance so vast that bridging it will likely take centuries. And yet, tonight, you can step outside and look up. If you are far enough south, you might find the constellation Centaurus, somewhere within that patch of darkness, invisible to the naked eye. A small red star quietly burns. Around it, a world roughly the size of Earth moves through its orbit. It is closer to you than any other planet beyond our solar system. The nearest possible shore across an ocean that stretches for 100,000 light-years in every direction, and still, it is so far away that every machine we have ever built, every engine we have ever ignited, every speed we have ever reached falls short by margins that feel almost unreal. Not because the universe forbids the journey, but because the journey asks for more than we have ever created, more than we can create today, and perhaps more than we will create for a very long time. And maybe that is where the story settles. Not in urgency, not in answers, but in scale. The quiet kind of scale that does not need to rush, the kind that stretches time, softens questions, and reminds us that distance is not just something to cross, but something to understand. So as the night deepens and the sky grows still, you can let that thought drift gently with you. Somewhere out there, beyond everything familiar, the nearest star waits, not calling, not fading, just existing, at its own pace, in its own time, and for now, that is enough.